Hi and welcome to this video, which is the introduction to differential calculus. So in this video we're going to look at just a basic introduction to calculus and the basic rules and so on. So we're not going to be covering any trigonometry, so that's important to note. So in the video we're going to cover examples of how to use differentiation to find the slope of a function, to use differentiation to find the equation of a tangent at a point on the function, to find a point on the function given a slope. So we're going to work with all of these just with our basic polynomials, so x to the power. We're going to use the product rule and then the quotient rule. We're then going to work a bit more with the rules of indices. We're going to differentiate e, we're going to differentiate log to the base e, and then finally we're going to look at calculating second derivatives. So there is a follow-on video which will look again at more of an introduction to calculus, but looking specifically at stationary points and how we would work with those. There will be further follow-on videos available which will go through trigonometry and anything else that was not covered, so rate of changes, etc. So let's talk about the derivative of a function. So the derivative of a function is written as dy dx when a function is given in the form y equals, and this means the derivative of y with respect to x. So generally we say differentiate y with respect to x, and we call that dy dx. So we can also write the derivative of f dash of x when the function is given in the form f of x, and that is pronounced f dash of x. So generally a good rule of thumb is if you're given the y, answer with dy dx. If you're given f of x, you answer with f dash of x. Sometimes you'll be given neither and you'll work through whichever way you want, but that's just a general rule of thumb. You won't be marked down for using the other form. So first let's discuss the derivative as. So one way we can think about the derivative of a function, and the first one we're going to focus on, is slope. So when we differentiate a function, we're finding its slope or its general formula for the slope. So when we find the slope of a linear function or a line, we get a numerical answer, which is a constant, because the slope is constant. So a linear function or a line has one slope for the whole thing. When we find the slope of a curve, we get a formula. So let's take a look at the slope of a curve. So here's the function f of x is equal to x squared plus x minus 2. So there are a number of points marked on it, so you should be able to see A, B, C and D. And if we talked about the slope of this curve, the answer would be, well, it depends. It depends on what point we take. So if you take the point D, or the point C, or the point B, or the point A, they'll all have very different slopes. So let's work with point A for a second. And what I've put in here in blue is the tangent to the curve at that point. So that means a line that touches the curve once and only once. So when we get the slope formula, so when I differentiate f of x and I get my f dash of x, that is the slope of this particular function, this curve, but it will be in terms of x, so it'll be effectively a formula. So to figure out the exact slope at that point, we would have to sub in our x values. So a you should be able to see is the 0.24, so at the point A, x is 2. So that is also equal to the slope of the tangent at that same point. So we're going to see those kind of phrases used interchangeably: the slope at a point or the slope of a tangent at the point. So now I'm going to show you quickly the page that we need to look at. So it's page 25 in your log tables. And this is going to be what we're going to focus on in this video. It is our basic rules for differentiation. So on the left hand side, we're going to deal with, and I'll highlight them so we can see them. We're going to use the most basic rule here, which is x to a power. We're going to use the natural log, ln. We're going to use all these versions of e. Now, that's as far as we're going to go here, but we are going to use the product rule, the quotient rule, and a few different versions of the chain rule within this video as well. There are, like I said, follow-on videos which will deal with basically what's missing here, which will be the differentiation trigonometric identities, and also working with rates of change. So let's get into a very basic example. So find the slope of a polynomial at a given point. So it says find the derivative of f of x is equal to 6x cubed minus 3x squared plus 4, and hence find f dash of 2 and interpret the result. So the first thing we're going to do is we're going to start with our f of x. So here is f of x equals 6x cubed minus 3x squared plus 4x. So using the very first rule, which is x to the power of n differentiates to n times x to the power of n minus 1. In short, what that means is when you differentiate, you bring down the power and take one away from the power. So what that looks like is you bring down the power and you take one away from the power, so that becomes 2 minus you bring down the power and then you take one away from the power, and then again you bring down the power. Remember, this is actually a power 1, so that's 1 times 4x. Now if I take 1 away from 1, I actually get 0. So what this works out as is 18x squared minus 6x, we don't write the power 1, and anything to the power of 0, if you remember your rules of indices, is 1, so this just gives me plus 4. Now eventually you'll probably get to the point where you'll go straight from the first line to the last line, and as we work through the video I will be doing that, but just for a quick reminder of how it works. So then it says hence find f dash of 2. So what's happened here is we had f dash of x, we now have f dash of 2, so they've replaced x with 2. So we're going to do the same. So everywhere there's an x, we're going to sub in our 2. 6 times 2 plus 4. So that is 18 times 4 minus 12 plus 4. That equals 72 minus 12 plus 4, which turns out to be 64. Okay? And then it asks us to interpret this result. So this is equal to the slope of f of x when x equals 2. Or you could also say it's the slope, so it's kind of like option 1. The second option we could talk about, slope of the tangent to f of x at the point when x equals 2. So we don't know the full point, but we do know when x equals 2. So let's take a look at a second example. So finding the equation of a tangent to the curve at a given point. So we are going to utilize some other pages in our formula book. So we're going to look a lot at our indices and logs page, but also we're going to work with our coordinate geometry page, because when they talk about the tangent, and in particular finding the equation of the tangent, we're going to work with page 18 in your log tables, which helps us with regards formula for that. So find the slope of the tangent to the curve y equals 3x squared plus 4x minus 5 at the point 1, 2, and hence find the equation to the tangent at this point. Okay, so they gave this to us as y, so we're going to answer it as dy dx. Bring down the power, take 1 away from the power, so that gives me 6x. Bring down the power, take 1 away, and that's plus 4. Now, when I have a constant, it effectively disappears, and the reason for that is that minus 5 could actually be written with x to the power of 0, because we know that anything to the power of 0 is 1. So if you bring down that power, 0 times anything is 0, so effectively it will disappear. So you don't need to show that, but you do need to bear in mind that any of my constants disappear. So now we want to find this at the point 1, 2, bearing in mind that there's my x value and my y value. So dy dx only requires an x value to be subbed in. So it's 6 times 1 plus 4, which gives us 10. And just to remember, this is the slope. And it is the slope of the function at that point, but it's also the slope of the tangent to the curve at that point. Okay, so that is what we've done, and now they've asked us to hence find the equation to the tangent at this point. So from page 18, I'm going to get my equation of the line formula. So there's two. So one is for building, the other is for when we're given the equation. So we're going to focus on the building one in the majority of these cases, and that is y minus y1 is equal to m bracket x minus x1. So the two things that you need when we're filling in this formula is your slope and a point. So my slope, I've just worked it out, is 10. And my point was actually given in the question. That's my x1, y1. So when we were filling in at that point back here, you might have wondered, well, we only need the x. Why have they given us the full point? Well, the reason they've given us that full point is because we now are going to use it to build the equation. So yeah, y minus 2 is equal to 10 times x minus 1. Let's multiply that out. X minus 2 is equal to 10x minus 10. You can rearrange this whatever way you want. I'm just going to I'm going to add a 2 to both sides. So I get minus 8. But if you prefer, you could write this as 10x minus y minus 8 equals 0, or in any form. If they don't tell you what form, they can't penalise you for not giving it in a form. Just make sure that there is no constants and then need to be added together. Once that's done, it's absolutely fine. So now let's take an example where we're going to find the points given the slope. So it says find the points, and I suppose always want to bear in mind words in the questions, and it says points, so I'm expecting plural. Okay, so that's important. If they said point, we're expecting one. They're little things, but they can help you a lot in questions, just to pick up on those little pieces. So find the points on the curve y equals x cubed minus 3x squared, at which the slope of the tangent to the curve is 9. So we're kind of working backwards here. We're still going to start with our y equals x cubed minus 3x squared. And they're talking about the slope of the tangent to the curve. So we know that that is differentiating, so it's our derivative, dy dx. Bring down the power, take 1 away from the power. Bring down the power, take 1 away from the power. So there's my slope of the derivative, and they've told me, or sorry, there's my slope of the tangent, and they've told me that this slope is, and the translation to maths of is always equals 9. Okay, so what we actually have now is a quadratic, so we're going to clean that up slightly. 3x squared minus 6x minus 9 equals 0. Two methods to solving a quadratic. You can solve it using guide number, which is a factorization method, or any other factorization methods you use, or you can use minus b. Now, I'm going to use factorization methods, so I want to simplify it. So I'm actually going to divide across by 3. So that gives me x squared minus 2x minus 3 equals 0. You can use guide number. I'm going to go straight to just my brackets because it's a nice simple one. And I have a minus 3 and a plus 1. And that'll get me my two answers, x equals minus 1 and x equals 3. So have I got my answer? Well, I've got the x part of the points. So they wanted full points. I've only got the x's. So we're going to go back with my x's and try to figure out, well, when x is minus 1, what is y? So I go back to my original equation, which was y is equal to x cubed minus 3x squared, and I'm going to sub in my minus 1. Minus 3 minus 1 squared. That gives me minus 1 minus 3, and that gives me minus 4. So my point is minus 1 minus 4. So my second point, x equals 3. Again, I want to find the y coordinate of that point, and it's still x cubed minus 3x squared. So I get y is equal to 3 cubed minus 3 squared, which is 27. 9 minus 27 equals 0. So my point here is 3, 0. So they are the 2 points on that slope where the tangent to the curve is 9. So just touching into this very briefly about real life functions, all I've done here is I've mixed up the letters, and it's just to show that it doesn't matter what the function is called or what the variables in it are, that you can still differentiate using the exact same rules that we've been working with. So in this case we have a equals 2k squared minus 3k. So in this case you can think of area, it could be a, and k could represent the length of some sort. So they want us to work with this area, or a, 2k squared minus 3k, and they want us to work out, differentiate a, so dA, with respect to k, dk. So dA, dk. Same rules apply. The thing is, you're always doing the thing that's given at the bottom. So differentiate a. So a is the full function with respect to k. So k is the thing that you are going to do the rule on. Okay, that's to bear in mind. K is the thing you're going to do the rule on. So just like with our x, so effectively k is our x. Bring down the power, take one away from the power, and bring down the power, take one away from the power. Simple as that. Just don't let the letters confuse you. We need to be able to do this with any particular letters, especially a higher level. So let's say k equals 1. So then dA dk, the derivative of a with respect to k, is 4 times 1 minus 3, which is 4 minus 3, which is equal to 1. Now, when we're dealing with functions like this, you may not be talking about it in terms of slope, but like I said before, that there will be further videos which will discuss this in a lot more detail. So now we're going to do a quick one where we're looking at working with the rules of indices. So again, if you have your log tables open in front of you, we're going to look at page 21, because we're going to need to work a little bit with this function before we can differentiate, and then we'll need to do a little bit of work afterwards. So it says find f dash of x, given that f of x is equal to 2 over the root of x plus the cubed root of x. So this shows some really good examples of where the rules of indices might be integrated into part of a question. So these are still functions with x's, however, because of the square roots, they look very complicated. So what we're always trying to do is to get these back to a point where I can use my rule, bearing in mind that the most basic rule for differentiation is bring down the power, take one away from the power. So I want everything as x to a power. So going to page 21, we can see that actually the square root is x to the power of a half. Now I'm going to keep this fx so we're not confused. I haven't differentiated yet. I'm not differentiating yet. All I'm doing is I am manipulating and using my rules of indices to get everything as x to a power. So then cubed root is x to the power of a third. So nearly there. The next thing I need to do is to bring that x to the power of half above the line. Okay, so that is rule or law 5 on that page. It says a to the power of minus p is equal to 1 over a to the power of p. So that becomes 2x to the power of minus a half plus x to the power of a third. Now that everything is x to a power, I can differentiate. So when I'm differentiating, my rule applies, and I probably will show this one. I won't power through it as quickly as we did the other one. So you bring down your power, and then you have 2x, and then you take 1 away from your power. Now I'm actually even going to show that, because this tends to be one that students do wrong a lot of the time, because they're trying to do things in their head, which is great, but things then can go a little bit wrong. So now that you can clearly see it, if anything goes wrong, at least anyone who's correcting your work knows exactly what you were thinking. So I get here minus x, because I have a half by 2, and minus 1 minus half is minus 1 and a half. However, we're going to stick with indices always to a top heavy fraction, so that is minus 3 over 2. Here I get 1/3 x to the power of minus 2 over 3. So that is my f dash of x. However, in a question, unless you were going to do something with that, which in this question we're not, we're just looking for this f dash of x on its own, we need to turn it back into something which we are more likely to see in a question. So the general rule would be to make sure that there are no negatives or fractions in our powers. So what we're going to do, we're going to again go back to page 21 and use our rules of indices. So we end up here with minus 1 over x to the power of 3 over 2. So we're using again law 5, bringing it underneath the line, plus again here 1 over, remember 3 is already on the bottom line, so it's 3 to the power of 2 over 3. So when I have a 1/3, that 3 is already in the bottom line, so I'm just bringing the x down to meet it. So now I'm going to go back to my log tables, and we have both, well, we have two different fractions, but they are both fractions. So 1, 2, 3, 4, 5, 7. So we're in law 7 here, which tells us a to the power of p over q is equal to the qth root a to the power of p. So what that means is I have minus 1 all over the square root of x cubed plus 1 over 3. Here it's the cubed root of x squared. So it's always the bottom line goes as part of the root now. You can, if you want, flip these around. So 3 times the cubed root of x squared minus 1 over the square root of x cubed. Now that last part completely optional. Generally we will put a negative in the middle rather than the start because it's very easy to lose a negative at the start. But either those second last or the last line will be acceptable as your answer. So I'm back on my log tables, page 25, and the reason I'm back here is because we're going to look at some other rules now. So we're going to look at the product rule, the quotient rule, and the chain rule. So first one we're going to look at is this product rule. So product means multiply. So when you have two functions multiplied together, you can of course multiply them out, but sometimes that's going to be a very long, tedious task. And if you start multiplying out big brackets, it can be very time consuming, but it can also be very prone to error. So we have a little rule here, which is if y is equal to ux, say it's two things uv, there are two things multiplied together, then dy dx, so the derivative of y is equal to u, the first part of the function, times dv dx, so the derivative of the second part, plus v, the second function, du dx, the derivative of the first function. So let's take a look at an example of how we could use this. So if y is equal to 6x squared plus 2x times 3x minus 2, find dy dx. So yes, of course, you can multiply them out, but it won't always be nice and straightforward like that. And like I said, it's very easy to get things wrong when we're doing some multiplication. So instead what we're going to use is we're going to use when y is equal to uv, so there's my u, there's my v, we're going to get dy dx as u dv dx plus v du dx. And do make sure you lay out your question properly and that it's very clear for someone to understand. So I'm saying my u is equal to 6x squared plus 2x. So then my derivative of u with respect to x, so du dx, is bring down your power, take 1 away from the power, you get 12x plus 2. And if something goes wrong there and it messes up the question, you're not going to lose as many marks because it's so clear what we were doing. So it's just going to be more of a slip or a misunderstanding. So it's really important that you show your work. So there's my u, my du dx, my v dv dx. The number of students who I see that just write down 12x plus 2 and don't explain what it is and then use it wrong. Like they are not using it correctly because it's not labeled properly. So get in those habits. So my dy dx, I'm going to come back over here first. Dy dx is equal to u, which is 6x squared plus 2x, times dv dx, which is 3, plus v, 3x minus 2, du dx, which is 12x plus 2. Now we are going to multiply this out, so you get 18x squared plus 6x. So you can bring this aside and work it out the long way. I'm going to do it quite quickly. So we have 36 x squared plus 6x minus 24x minus 4. Let's add what we can. So there's an x and an x and an x. There's an x squared. Oh, and an x squared. So 54x squared plus 12, so minus 12x minus 4. And that is our final answer for dy dx. So our multiplication, we still had some multiplication to do there at the end, depending on the question. Sometimes you just need to sub in, so maybe multiplication wouldn't be required, or the multiplication would be simplified quite a bit. But bear this in mind that we do have this product rule, which can make your life much simpler. The second rule we're going to look at is our quotient rule. So that is if I have two functions u and v and they're one over the other, or division. So just to link you back, to make a connection here, the cue that we have for rational numbers, think way back to your number systems. Rational numbers are numbers that can be written as a fraction. They're the opposite to irrational numbers. So rational numbers had a cue, and I suppose if you didn't, or if the connection wasn't made for you at the time, you can make the connection now that actually stands for quotient, so that division. So quotient is another word for division, and think of what kind of numbers have division inbuilt, and it's fraction. So that line in the middle means divide. So it's two functions that are dividing, well, one dividing into the other. So let's use our quotient rule. So again, I'm just going to write my function, or my quotient rule up here. Y is equal to u over v. So my dy dx. So in the last one, the product rule, they were adding, so the order wasn't as important. Now it is super important because we're subtracting u dv dx. So it's important that that one is subtracted, and that's all over v squared. So just like before, I'm going to set my u is there, my v is there. So u is equal to x squared plus 7. So du dx is equal to 2x. And v is 3x minus 1. So dv dx is equal to 3. So I actually have f of x, so I'm using f dash of x. So that's all I'm going to replace here. V is 3x minus 1. Du dx is 2x minus u, x squared plus 7 times dv dx, which is 3, all over v, which is 3x minus 1, and that is squared. Okay, so let's work this out. 6x squared minus 2x minus 3x squared minus 21, all over 3x minus 1 squared. And hiding that up, you get 3x squared minus 2x minus 21, and that's all over 3x minus 1 squared. So that's pretty much as simple as it can go. The top line can be factored, but it won't factor into a 3x minus 1, so it definitely won't simplify down. So what I'm going to do is I'm going to multiply out the bottom line. So I get 9x squared, so square the first, twice the first by the second, so that gives me minus 6x, and then square the last, which is plus 1. Now again, this is probably going to be in the middle of a question, so you won't be kind of questioning, should I multiply it out? The rule is, if they ask you to do something else, the form in the middle of the question can't really be examined in great detail. So unless they've specifically asked for it in a form in the middle of a question, you can do whatever you want. You don't need to multiply it out. If it was substitution, obviously multiplying it out is going to be the much longer route. So bear all that in mind. So visiting back to page 25 again, this time we're going to look at the chain rule. So the chain rule is basically a function within a function. Now this is one that, yes, we have a formula here, but I tend to really not use this formula so much. and I would advise students to generally get a sense of what's happening with the chain rule. The reason I say that is because the product rule and the quotient rule, even if you've only tried it once, you'll probably make a really good attempt at using it again. And the problem with the chain rule, I think the formula is not very clear unless you really understand what's going on. And if you really understand what's going on, you probably won't use the formula in here. So I'm going to work it without the formula, but let's just take a look at the formula for a second. So basically this is where there's an inner function v of x, which is part of a bigger function u. Okay, so it is basically, if we think back to our functions, it is a composite function, so a function within a function. So what you do is you differentiate du dv, so you differentiate u with respect to v, and then you differentiate v with respect to x, and you multiply these two answers together. What that ends up looking like is you differentiate the whole thing using our rules. So the rule is bring down the power, take one away from the power, and then you multiply it by the derivative of the inner function. So let's take a look here. So the chain rule is usually seen at the start anyway with a power, so a bracket to a power. So what we do is we treat this bracket like it's one thing, like it's our x. So for example, for dy dx, we would literally treat this bracket like we would treat an x. We bring down the power, so 2x squared minus 1, and we take 1 away from the power. Now, the thing is, it isn't an x, it has a whole bracket. So then to correct this derivative, and that's the way I like to think of it, we then have to differentiate the inner part of the function, so inside the bracket. So that becomes bring down the power, take 1 away from the power, so you get 4x, and the minus 1 disappears. So you're multiplying that by 4x. Okay, so that is the chain rule. So you differentiate the whole thing with the rule. So bring down the power, take 1 away from the power. But because it isn't just an x to the power of 3, because it's a whole bracket to the power of 3, we need to do like a correction, and that correction is differentiating the inner bracket. So let's tidy this up. So 3 by 4 is 12x, and unless they tell me I am not going to square out my bracket and do that multiplication, I'm going to leave my answer just in this form. Again, bear in mind that when we're using these kind of rules, they're in the middle of a question, and what form it's in won't really matter. So this is another example of the chain rule, and straight off you might go, oh, but it's not a bracket to a power. But if you go back to page 21 and think back to your laws of indices, you'll hopefully remember that the square root actually means power of a half. So we get an answer something like this. So to differentiate my dy dx, I do the chain rule just like I did before. I bring down the power, and I take 1 away from the power. So I have a half minus 1, which gives me minus a half. However, because that was a full bracket, I now have to multiply by the derivative of the bracket, which is 6x. So I'm going to tidy that up. I'm going to multiply the half by 6x. That gives me 3x. And then, because it has a negative power, and we discussed this, it really shouldn't have a negative power. So we want to change that. So we'll bring it underneath the line. So we get 3x squared minus 2, and that's all to the power of a half. It also shouldn't have any fractions in the powers, so we're going to change that into the square root of 3x squared minus 2, and that will be our final answer. So now let's look at an example of using the chain rule within other rules. So the chain rule can often be seen slotted into other rules. So here, for example, if y is equal to x all over the square root of 1 minus x, evaluate dy dx when x is equal to minus 3. So first off, I'm seeing two functions, one divided by the other, so therefore I'm thinking quotient rule. So y is equal to u over v, so then to get dy dx, I have v du dx minus u dv dx all over x squared. So I set this up like a normal quotient rule. I have my u is equal to x, so du dx is 1, and my v is equal to square root of 1 minus x, which I can't work with, so instead I have to get rid of that square root and write it as a power of a half. Now, that's better. So when I differentiate dv dx, what I'm actually doing is using the chain rule. So I have a half times 1 minus x, and I take 1 away from the power, so that'll give me minus a half, times what's the derivative of what's in the brackets. That gives me minus 1. So cleaning that up, I get minus a half, 1 minus x to the power of minus a half. Now, for a question like this, it's completely up to you. We have a negative power and a fraction, so it's going to be, we're going to have that 1 minus x underneath the line, and it will be a square root. Now, because we're only in the middle of the question, if you want to change it to that, that's absolutely fine. I'm going to leave it like this for a minute while we do our substitution, and then we'll be able to clean up. Apologies, I just realized I have an x squared there. That should be a v squared. So let's go to the let's go back to the quotient rule formula and sub in. So my v is equal to root 1 minus x, and du dx is 1, minus u, which is x, times minus a half, 1 minus x to the power of minus a half, all over v squared, square root of 1 minus x squared. So let's do some cleanup. So top line, 1 minus x, that's fine. Minus by a minus is a plus, so I get plus x over 2. And I'll have 1 minus x to the power of minus a half, and that's all over 1 minus x. Okay, so it doesn't look so bad, but that top line is going to need an awful lot of work. So I'm going to take that top line and I'm going to work it through here for a second, just because in a fraction it can be a bit of a nightmare to work with the fraction the whole way down the page. So I'm just going to take my top line, x over 2, 1 minus x to the power of a half, and see what I can do with it. Sorry, it's a negative half. So there's nothing I can do with that first part. However, the second part is going to be x all over 2 the square root of 1 minus x. So it became 1 minus x underneath the square root because of the half, and it all went under the line because of the minus. So now I'm going to try combine this, because what I'll have is a very complex fraction. So I'm going to multiply 2 root 1 minus x times root 1 minus x plus x, and that's all going to be over 2 root 1 minus x. So common denominator was 2 root 1 minus x. That first term had a denominator of only 1, so it needs to be multiplied out. So effectively I have root 1 minus x by root 1 minus x. That becomes 2 times 1 minus x plus x all over 2 root 1 minus x. And that gives us 2 minus 2x plus x all over 2 root 1 minus x. And that gives us 2 minus x all over 2 root 1 minus x. So that goes back in as my top line. I'll just box this off. So that equals 2 minus x all over 2 root 1 minus x, and that is all over, so I'm just going to use a divide sign, 1 minus x. So I've just cleared the page here to have a bit more space. So effectively what you should have now is 2 over x all over 2 root 1 minus x all over 1 minus x. So this is the big division that we had on the previous page, and we're dealing with complex fractions here. So what I'm thinking is, well, I can't divide by a fraction, so instead what I need to do is I need to multiply by the reciprocal. So I have divided by 1 minus x, which I can't do. So instead what I do is I multiply by the reciprocal, which is 1 over 1 minus x. So that becomes 2 minus x times 1 all over 2 times 1 minus x root 1 minus x. So 2 minus x, we can multiply this out, 2 minus 2x square root of 1 minus x. Not a huge amount I can do with that, so that's as simple as it can be. Now, that is as far as we need to go. That is our dy dx. So I'm just going to put this up here. So we have dy dx equals 2 minus x all over 2 minus 2x square root of 1 minus x, and we want that specifically when x equals minus 3. So let's take this for a second. So we want dy dx equals 2 minus minus 3. 2 minus 2 times minus 3 square root of 1 minus minus 3. And that can all go straight into the calculator, and when we do that we should get our answer of 5 over 16. So back on the log tables, page 25, so I'm going to go back to my rules here on the left hand side, and we're going to look now at working with e. So e to a power. So remember that e is a constant, so you can type it into your calculator. It's 2.71. And this is an interesting one because in the log tables it says e to the power of x. When I differentiate, it stays e to the power of x, and that is true. Nothing happens. The next rule says e to the power of ax differentiates to a e to the power of ax. And when a student sees this for the first time, their reaction is usually, so whatever the coefficient of the power is, we bring that down. And that's not necessarily true. This is actually a version of the chain rule, and instead of a being the coefficient of x, it's actually the derivative of the power. So it's the derivative of ax. So if I have 4x and I differentiate, I get the 4. So yes, it looks like the coefficient, but it's actually the derivative. So you might say, well, does it actually really matter? That sounds a bit like, you're being a bit pedantic, looking at specifics that we don't need to know, but actually you do, because as we work through it, the difference will happen when I don't have just an x, where it becomes an x squared, and we'll see some examples of that. So let's look at an example of just that. So differentiating e using the chain rule, so dy dx. So given that y is equal to 5e to the power of x squared, find dy dx. Now the thing about dy dx is the piece that we started with when we're talking about e's doesn't change. So we are going to keep this exactly as is. All that we need to do with that is multiply it by the derivative of the power, which is 2x. So if you thought in your log tables that a, so meant the constant, or that a, when we were talking about ax and then the a comes in front, that meant the coefficient, you might think, oh well, I'll multiply this by 1. But that's not necessarily true. So it's important to understand the difference here. So we get 10x e to the power of x squared. And that's our final answer for dy dx. So this is a version of the chain rule, because we treat this exactly like we would treat it, which is just no change for e's. And then because it's not just an e to the power of x, we then have to do like a correction by multiplying it by that inner function. So the x in that power, we have to differentiate that to get our answer. So here let's take a look of e within a chain rule. So this is the traditional chain rule that we have seen. So y is equal to e to the power of x plus 1 all to the power of 4. So the chain rule, which basically says differentiate the bracket, so bring down the 4 to that power and take 1 away from the power, so that leaves me power of 3, but then differentiate by what's in the power. So e to the power of x goes to e to the power of x, and 1 goes to 0. So we get final answer 4e to the power of x, e to the power of x plus 1, all to the power of 3. Now, you would not be expected to multiply that out. It is perfect as is. So, back to our log tables again, and we're going to look at our final rule from this page, which is differentiating the natural log. So, ln x, a natural log, or it can be log to base e of x. So find dy dx given log to base e of this. Now again, this is a version of the chain rule. In my log tables, start with y is equal to log to base e 4x squared plus 1. So in my log tables, it has just given me a log to base e of x. So when I differentiate, I follow my rule. It'll be 1 over whatever is here, 4x squared plus 1. However, because this thing is not just an x, I have to correct it. So what I do to correct it is I multiply by the derivative of what's in the bracket. So that gives me 8x and the 1 disappears. So that gives me a final answer of dy dx as 8x all over 4x squared plus 1. You will be using the chain rule so much in so many different places that it's important to notice that it's the chain rule. You're not trying to think of, oh, and I have this rule for e and I have another rule for logs and I have another rule for this. They're all versions of the chain rule. So if you can really understand what you're doing in the chain rule, you're going to find this all a lot easier. As you move on and look at trigonometry, they are also using the chain rule. So now let's look at another example of differentiation in natural log, so working with the chain rule. So given that y is equal to log to base e of 1 plus x all over 1 minus x, show that 1 minus x squared dy dx equals 2. So it's important here to note that we are looking for dy dx, that is our purpose, and we're going to sub it into that formula there. Now, if we're looking at y is equal to log to base e, we're going to be doing 1 over whatever's in the bracket, but remember it's a version of the chain rule, so we need to multiply it by the derivative of what's in the bracket. So I'm already thinking, well, if I had to multiply by the derivative of what's in the bracket, that becomes the quotient rule, which is quite complicated. So instead what I'm going to do is I'm going to use the laws of logs, in particular law 2, to separate out what we have here for y. So that actually becomes log to base e of 1 plus x minus log to base e of 1 minus x. And now I have something much easier to differentiate because all I have to do is do 1 over whatever's in the bracket and multiply it by the derivative of the bracket, which in this case is 1. Again, 1 over what's in the bracket multiplied by the derivative. Now, when I differentiate 1, it disappears. When I differentiate minus x, I get a minus 1. So what we get is 1 over 1 plus x plus 1 over 1 minus x. So what I'm going to do to simplify this is I'm going to get a common denominator. And my common denominator is going to be 1 plus x times 1 minus x. And I will get 1 times 1 minus x plus 1 times 1 plus x. I'm going to clean that up. So dy dx equals 1 minus x plus 1 plus 1 plus x. I'm going to square that bottom line using difference to squares. It's going to square the first minus square the second. Okay, so I get dy, so let's move it up here, dy dx equals, my x's here cancel, and I put 2 over 1 minus x squared. So they want to show that 1 minus x squared, then dy dx equals 2. So what I'm going to do is I'm going to do 1 minus x squared instead of dy dx, so then 2 over 1 minus x squared equals 2. I have some cancelling happening. 2 equals 2, which is, 2 equals 2, which is exactly what they want, so QED. So now let's talk about the second derivative. So a derivative basically gives you the slope of a function at any point. And the second derivative is the derivative of the derivative function. So what we're going to do is you first find the derivative of a function and then take the derivative of that. So it's the derivative of the derivative. So you differentiate what you've already differentiated. So you differentiate something twice. So the derivative is given as f dash of x, and the second derivative is given as f double dash of x. The derivative can also be written as dy dx, and in that case the second derivative will be given as d2y dx squared. So that's how it's pronounced. d2y dx squared. Remember, the first derivative gives the slope of a function at any point, and the second derivative gives the rate at which the slope is changing over a given interval. It'll be used more in context as we look at stationary points and real world examples. So for now we're just going to focus on how to do the second derivative, how to calculate it. A bit more on the practicalities of how it's used will be done and covered in later videos. So given that y is equal to x plus 1 over x, find d2y dx squared. Okay, so y is equal to x, now plus x to the power of minus 1, because I need everything as x to a power. So I'm going to differentiate that, which is dy dx, and I get 1. Now here I get plus. Bring down the power and take 1 away from the power. Be careful, take 1 away from minus 1 and you get minus 2. So you get 1 dy dx minus x to the power minus 2. Now usually we will get rid of that negative 2 and put it as 1 over x squared, but because we're not looking for dy dx in the middle of a question, we're looking for d2y dx squared, we'll leave it as is. So dx squared. So 1 disappears and you get minus, bring down your power, minus 2, take 1 away from your power, minus 3. So we get 2x to the power of minus 3. So that's second derivative. So final answer, cleaning that up and bringing that 3 under the line, is 2 over x cubed. So now just one that works a bit more with a differential equation here. So y is equal to 3 over x plus 4x. Find dy dx. Okay, so they've asked us to find that, and d2y dx squared, the second derivative, and hence show that x squared d2y dx squared plus x times dy dx minus y equals 0. Now, because they asked me to get dy dx and d2y dx squared, I will make sure that both of them are in a nice form to finish off. So let's start with y. So again, over x doesn't work for me, so I'm going to do x to the power minus 1 plus 4x. So dy dx equals minus 3x to the power of minus 2 plus 4. Now I'm actually going to work through over here, and I'll explain why in a second. So I'm going to clean this up, and I'm going to do 4 minus 3 all over x squared, and that is my first derivative. Now, but if I was to take that first derivative and work with it, I'd have to transfer it back into x to a power. So that's why I moved it slightly to the side to clean it up. So now I can differentiate this for the second derivative quite easily. So I get 6x to the power minus 3 plus 4. Sorry, the plus 4 disappears because it's a constant. And what we get is the second derivative is equal to 6 over x cubed. So we want to show that this is true. So let's work that. So x squared times 6 over x cubed plus x times 4 minus 3 over x squared minus 3 over x plus 4x should equal 0. So I like to work with my functions with the powers as positive and them underneath the line. I think it's a bit easier, but you can of course work the other way. So that gives me an x, and that cancels here. So I get 6 over x plus 4x minus 3 over x. So what's happened is I get 3x over x squared, and when the x's cancel, minus 3 over x minus 4x equals 0. So cancelling, they cancel here. I get 6 over x minus 6 over x equals 0. 0 equals 0. So that is true.